Today is chapter 11. That's what I ended up doing, and it's not bad because it is very important. So it's all about RS-232 or UART on the board. So we're going to be talking to our computer. So as an overview, I don't want to go into too many details about what the protocol is. That's it there. It looks like that. So RS-232, you can almost interchange it with UART. So UART stands for Universal Asynchronous Receiver Transmitter, which is usually what the peripheral and a microcontroller is called. The UART is what speaks to the computer. The computer is an RS-232 protocol. Really the only difference is the hardware signaling. So out of your computer, you come out at, it's like plus and minus, it's supposed to be 12 volts, but it's like 8 volts or something like that. Anyways, it's plus and minus something. And of course our boards are running 0 and 3 volts as our supply rails. So you have to do a level translation. And there's a little IC right near the UART connector that does that for us. So it's a little charge pump circuit. So it ups the voltage and inverts it for talking out, but it also buffers it and down converts it to our logic levels from the computer. So that's kind of the PHY, as they call it, the physical interface that the processor doesn't have on board, because I think it takes too much space and you gotta have a bunch of caps on there, so they don't bother incorporating that. Plus, if you're talking, most of the time if you're talking from one microcontroller to another microcontroller with UARTs, then of course you don't need that translation. But if you want to talk to a computer, then you stick one of those rather expensive, for some reason, chips on there. So you can check out the hardware for that. So probably throughout today's lecture and for all time, I'll say UART, or I'll say RS-232, or I'll say serial, all the same thing pretty much, because we're worried about the logical signaling. So this is what it looks like. In an idle state, you've got the minimum you need for UART, other than power and ground, is a transmit and receive. Okay, so it's a full duplex capable transmission, so you can talk and listen at the same time, because each device has its own transmit line and a receive line. So there's two communications lines, transmit and receive. Be careful when you're hooking up transmit and receive lines, because sometimes you get a bit mixed up, because you'll come across situations where the transmit line from one device will hook up to the transmit line on another device, but somewhere else the transmit line will hook up to the receive line. And it just depends on the perspective that they've decided to name their pins. And I have blown boards, not blown boards, but had to redo boards because I wasn't careful enough in making sure where transmit goes and where receive actually goes. So be careful with that. There's also something called a null modem cable. I thought I had a serial cable with me. Weird. I'm sure I brought it over. It's probably sitting in the other lab. But hopefully you've all seen the serial cable. So it's got the connector that is on these things called a DB9 connector. So it kind of looks like this, and there's 5 pins and 4 pins. So DB9. So you'll see that all over the place. So a cable that connects to that is just a serial cable. Most cables are straight through, so all the pins go, so pin 1 on here goes to pin 1 on the other side. Your transmit and receive pins, whichever, if this is pin 1, 2, 3, 4, 5, I think they're usually numbered like this. There's a diagram in the notes. So 1, 2, 4, 5, 6, 7, 8, 9. This is usually transmit and this is usually receive, 2 and 3. The other pins have some functionality, but you don't usually use it, but you can. There's some situations where you can for some hardware flow control. A regular straight-through cable, TX, will come through TX on the other one, but there's something called a null modem cable or a crossover cable, where these two are swapped in the cable. So that means that pin 2 on one end routes to pin 3 on the other end. And the worst part about null modem cables is that most of them look exactly like the other ones. So you go to your office and you'll be like, why isn't my serial connection working? And I've also killed many, many hours troubleshooting UART firmware when it's someone who has put a null modem cable. So I'm quite religious at putting a piece of tape that says this is either straight through or null modem cable. I'm going to build a little device, so you'll see it on the Engenuics page. That's just a quick plug-in check for that, because you can waste hours figuring that out. Some null modem cables actually have an X on them, or will say null modem. Buy those ones, so then you won't be confused. So that's the physical connection, covered signaling. That's pretty much all there is to. We're not going to talk about the other pins. You can look that up. You'll come across it for flow control, so we won't worry about that because we won't use it. For the logical level, if you're just looking at one particular signal line, most of the time in an embedded system, even though you can run full duplex, you kind of let one device talk and another device listens and talks back. So you're exchanging data back and forth separately, sort of like a half duplex, even though you have that full duplex capability. But the signaling works on the same line, or the same way for both lines. So you always start in the high state. So considering that this is on the board, you'll be at VCC, which is 3 volts on our system, and that's the idle state. Now, you can bit bash UART protocols, and it's not that bad of a thing to actually code specifically to figure out how to implement this protocol. We're going to use a peripheral that does it automatically. So we'll kind of talk in the context of what the peripheral probably does in decoding what this is. And if you were doing it, if you were bit bashing it, you'd probably do it in a similar way. So you could look for a falling edge, so you could use an edge detector, like an interrupt on an edge, to look for that. So that's the start of communication. So that's when a device is saying, I'm about to send you some data. The worst part about UART is that it is an asynchronous communication protocol, which means that device 1 over here, device 2 over here, so they've got TX and RX. TX, RX, I'll just hook them up straight across. And again, you can see why that can be confusing. Each of these devices separately is responsible for generating the clock that clocks out that signal. So that's what makes it asynchronous. There's no clock transmitted in the signaling itself. There's advantages and disadvantages to that, probably more disadvantages, which is why there's a lot more protocols that either use the clock, send clocking the signal, or have a separate clock line, and we'll see some of those. But what this implies is that both of these devices, before they ever start talking, they have to know the parameters of the communication. So they have to know what's called the baud rate, or essentially the communication speed that's going on. Has everyone configured a serial port, like a terminal program on the computer at one point in their lives? I hope that you have. It'll do it today if you haven't. So a very common baud rate is 9600, which is pretty slow. A faster one is 576K, and you can go up to, I think in Windows it says you can go up to about 115 kilobyte per second, which is pretty fast, and then you can do some higher speed UART speed. Because of the physical setup of this protocol, you're limited to a certain speed, so you probably can't do a megabit per second because the hardware isn't set up for that. So 9600, because if you're not sending a lot of data, 9600 is a great frequency to use. It seems to be somewhat standard for everything you use. A lot of devices do use UART still, so every GSM module that I've worked with, every GPS module that I've worked with, they both have as a standard interface is UART, and they usually default to 9600 baud. So there's that. So both of these have to have the same baud rate. There's a configurable number of data bits. Usually you send 8 data bits, which makes sense because it's a byte, right? There's a configurable number of stop bits. Most of the time we use 1 stop bit. And you can also do things for error checking, like a parity bit and things like that. So the very common setup that you'll see is 9600 BPS, which is your baud rate, and then 8, none, 1. So 8 data bits, no parity, 1 stop bit. You'll say that all the time. What's your protocol? Oh, I'm 96, 8, and 1. And you'll see that in text. So that's what that means. And then there's also flow control, which uses some of those additional lines on there, and that's usually off. So no flow. Okay. So both these devices have to have those parameters set before they start transmitting. There is this thing called auto-botting, and it never works, so I'm not going to talk about it. Yeah, it really never works. as far as this signaling goes, so we've already talked, we get this edge detector, which means that it triggers the listening device to start listening and to start clocking out this data. So the first thing it does is it'll sample, sees this edge, it knows what rate it's going at, so whatever period that ends up being, it's almost whatever it is. It'll know what the halfway point is of that, and it'll take a sample of the line at the halfway point. So a start bit, as it's called, is a low bit. So you get a trigger, and the first thing it looks for is a start bit. So by the protocol definition, you should have a 0 first. Okay? If it doesn't, then you have an error on your bus. As long as you've got the right start bit, then it'll continue to sample on each of the next intervals for however many data bits you've specified there. So as long as your clock is correct on both sides, this frequency is the same on both sides, then this sampling point is going to wind up right smack in the middle, and you're not going to have any problems. Once you get to this bit here, so this is the 10th bit in the transmission, it has to be high. So it's called a stop bit. So this has to be low, this sample has to be high. If that's true, that particular data byte is considered good. It won't flag any sort of error on you. Now, lots of problems here. Data bytes, you don't know if they're high and low. Without any built-in error checking, there are so many problems that can occur with this that you might think that it's a very unreliable protocol, but it tends to work quite well. If you need to add some robustness, then you tend to kind of add your own things, and usually you do it within the messaging protocol that you'll use that uses a UART transmission. So we'll see when we get to the ANT radio, their communication, even though we're not going to do it with UART, but they'll still send a bunch of data bytes that don't have individual error checking on them, but a message might be 15 or 20 bytes, and you'll have a checksum in there, and you can verify your message back there. If you start putting a whole bunch of parity bits and other error checking in here, then it just adds to your overhead. This is already only 80% efficient, right? Because you've got a start and stop bit, so 2 bits for every 8 data bits are just overhead. Okay, so it's not that efficient of a protocol. Okay, so if you want to start going high speed, then you've got to consider that in there. Okay. And that's enough of the protocol. So you'll see that if you bit bash your own protocol, it's kind of nice because you can actually flip an I/O line when you sample. So you can look at the communication line on an oscilloscope, and you can output your sampling period and actually see where you're sampling. If your clocks are different, or your clock is wrong some way, then these sample points are going to start drifting around there, so you can see if you've got some problems. If this is really super fast and you can't sample fast enough, then you'll see the drift in there as well. As far as the peripheral goes, you don't have access to when it's sampling. Some different peripherals work in different ways. They might try and take best of 3, they might do an edge detect, they might do a whole bunch of different things. I think this, I don't know if this one even comments on the ARM processor how it works, but a lot of them do just assume that the one sample that they take in the middle is correct. But if you have noise and stuff like that, then you can have some problems. So there's a bit more discussion about all the different issues that can come up with this sort of communication. Okay? There's not that many. For this lab, you'll notice that your boards will plug directly into the COM port, so you don't need a cable, you can plug directly in there. In the MPG directory, or the start menu, there's an IEEE MPG grouping. There's a program called TerraTerm, which is a much better terminal program than Windows Terminal. Windows Terminal is the worst program in the world for if you've ever tried to use it. So use TerraTerm or use your favorite terminal program. There's a billion of them out there. TerraTerm is nice and simple. Shows you how to set it up and all that to configure this. And throughout this whole lab, we're going to be outputting to TerraTerm so you can see what's going on the computer, and then you're going to be sending stuff to it. ASCII. Everyone know what ASCII is? I don't know what it stands for. American something blah blah. What you should know is that when you say U8 or char equals single quote A. Okay. Needs a variable name. We call it food. Because everyone calls it food, right? You make food. So this is just a number, okay, but you're using ASCII representation to load it into here. There's a thing called an ASCII table. You can go to ASCIItable.org or look in the notes, and it shows you what all the ASCII characters are. This just translates into some hex value. I think A is like 65, is that what it is? 64, 65, decimal or hex?
Decimal.
Okay, so you guys are well, you know this well. So this is decimal 65, and it's like OX40, right? Something like that, approximately. All the same thing, right? It's all the same number in memory, but you can choose to write it in different ways. That's different, right? With quotes, that's now a string, that won't work. Okay? So single characters for ASCII. When you're talking on serial port, especially when you're looking at a terminal program, when you are typing numbers, when you type the number 1, you don't send 1. You're sending ASCII 1. Okay? Now, ASCII 1 is, let's bring up the table so I don't just guess at this. Sorry. So ASCII 1 is decimal 49. So when you receive 49, assuming you know that you're talking ASCII, you need to convert that or display it as the ASCII code. If you load a number, so if I have a number U8 equals 1, oops, like that, I actually have the number 1 in there. Okay? If I try to print that to an ASCII type device, nothing happens. Okay? This is OX01, which is a control character. The first 30 or so characters of the ASCII set are control characters, so the computer will interpret them in different ways. You can make your computer beep, you can do a backspace, you can do a carriage return, all that sort of stuff. Those are ASCII codes. So if I want to print this out, I have to look at my table and say, okay, decimal 1, to convert that to ASCII, I need to add what ends up being OX30 all the time. So if you take 1 plus, nice writing, 1 plus OX30, that equals 1 in ASCII. So you end up doing a lot of translation. The worst part is when you have some big number. So if you're doing a calculation, and you're going to do this today, so part of the exercises is you're going to print a counter out under your name. So in memory, you're going to have a short value, or a 16-bit value, for a counter. And you're going to count that starting at 0, and you're going to go all the way up to 9999 before you roll it over. So if you've got 9999 in memory as an integer, to convert that and print it out to your terminal program, you have to parse that whole thing out. Okay? So you take 9999 in real numbers. There's some built-in functions that will let you go from an integer to ASCII or from an ASCII to integer. Only one of them is standard because, well, there's some problems, and I talk about that in there. What you really need to do is you have to parse this out. So you have to divide it by 1,000 to get that whole number. So you do a modulus 1,000 and get that number. Sorry, I guess divide. So you go divide by 1,000 and you get 9. And you take the remainder and divide. So the remainder is 999, and you divide that by 100 and you get 9. Each digit that you get, and you have to convert that to ASCII and prepare your number in an array of like a string, essentially, and then print that out. So this becomes a total pain in the butt when you're doing stuff. When you need to interact with a human user that only looks at ASCII numbers, because we don't do hex very well, or we don't do binary very well. it's a pain. So you write yourself a nice set of drivers, and then you just take care of that in one fell swoop, and then you've got the capability to do that. But doing any sort of functions where you have a multi-length number becomes a problem. And I'm going to be nice to you in this exercise. I'm going to allow you to do leading zeros. Okay, so when you're doing your counter, you're going to start at 0, 0, 0, 1. So you can write a pretty tight little function that has an array that's 4 characters long that you can just divide into these characters. You know to do it quite quickly. If you have to account for a variable length array, because if this is just 1 or it's just 99, 999, then you have to be able to account for that. And that's, so I2A is a, you'll see these around. I2A is a function, and A2I is a function. So this is a built-in C function, A2I, okay? Because that's easy. You can feed an ASCII string in and into this function, so you send the pointer of the function, and it will return the integer value to you, because it can do that. And all it does is look, it starts looking at numbers until, I think, the first non-numerical character, and that's what it returns to you. But I2A is not a standard function, and it doesn't exist. It does exist in C++ because C++ has a string class, right? C doesn't have a string class. There's no, string is just an array, and strings are notoriously problematic in C, but C++ solved that. So that exists in C++ because of the string class, not in C. That one exists in both. So that's the trouble with ASCII. And trust me, you will curse ASCII at some point in your career because you'll have to display this stuff and you're like, oh, I remember this in MPG. The UART Peripheral is pretty easy to use. So far, what peripherals have we done so far? We've done the PWM peripheral, we've done timer peripherals, GPIO is a peripheral, we've done that, and we've done interrupts. Okay? Every time we start one of these things, what do? Open the data sheet, read through the data sheet, figure out what the registers we need to work with are and what to set them up as. There's usually a couple things you need to spend a bit more time reading to figure out exactly. As far as the UART peripheral goes, pretty easy. The hardest part is figuring out the baud rate. So there is a rather horrendous calculation to get the baud rate set. So we want 9600 BPS. We have a 12 megahertz clock source. By spec, for this particular processor, and I think every single processor seems to work differently, the spec for this processor says I need to generate a clock that is 16 times faster than 9600. So 16 times 9600 is 100 and something thousand hertz. And so you need to divide 12 megahertz down into that. There's a couple of registers that allow you to do that, and sometimes you can get it bang on. For 9600 you can't. There's going to be a wee bit of an error in there, but you can get close enough. Okay. So for this processor, it's kind of a crappy UART baud rate generator, and you end up with an iterative process to get the right register settings. Iterative processes are bad. Iterative processes demand spreadsheets. So I built you a spreadsheet. So there's a baud rate calculation spreadsheet, and part of the exercise through the notes is to use the spreadsheet to get the numbers to generate the baud rate. You'll see about it when you read it. The other thing is with interrupts. You can do all your transmit and receive without interrupts, but I would highly recommend when you're doing communications drivers that you look at how to do them with interrupts, because it's much better. You can service very quickly incoming and outgoing bytes with an interrupt service routine and take a lot of load off your main program. You can save a lot of power because you can do a lot of sleeping and just let your interrupt handler wake you up, grab your byte, go back to sleep whenever you're getting transmissions. So I always kind of look for an interrupt-based solution for any sort of communication protocol. As I believe what I've done here, I decided to go for the receive. So as whatever bytes come into the microcontroller is interrupt-based, okay, because that makes sense. You never know when those are going to come in, so it makes sense to be able to have them on an interrupt. For transmit, we're just sending them out one character every time we go through our regular 1 millisecond loop. Okay, so it's a bit different. You kind of get a glimpse of doing it interrupt-driven and non-interrupt-driven with the way that I wrote the driver. And other than figuring out what interrupts to have, the UART has within it 4 or 5 different sources of interrupts, so you can do different things. There's some built-in buffers on this peripheral, which is nice. So you can, in hardware, there's hardware buffers that can read in a bunch of characters, and so you don't have to respond to every single bit or every single byte coming in immediately. And you can let them fill up, so you can sort of space out when you're going and receiving the actual characters. So you can interrupt when that buffer has 1 character in it, when it's half full, when it's almost full, and you can do a lot of neat things with that, which is kind of nice to have. We're not going to worry about adding that bit of complexity. We're always going to, as soon as we get a byte from the computer, we're going to go use our interrupt to go grab that and throw it into our receive buffer for our UART peripheral, and then we'll decide what to do with it. The application itself, we want to set up to, of course, be able to receive data coming in, but also give us a mechanism where we can just send out ASCII strings to a function, and then the UART application will take care of sending those to, right now, the terminal, and we'll probably make it point somewhere else, like the LCD later on, or do something very similar. So I will leave that the details of the UART application to the exercise, because that's a big part of this chapter, is just going through that exercise. I will tell you that I threw in a test application, or a test feature in the application. So that's something you do all the time when you are doing programming. So you'll write a driver, and of course you want to be able to just test the driver before you throw it out and let it go into the real world to be used. So there's a little application in there that when you press the button, this is the usual, you can't see this because you're out there, but when you press and hold a button, it'll just start, it's not a random character output, it starts from the first printable character and goes through the whole printable character set, and as soon as you release the button, then it stops and does a line feed. So that's part of the test application, so that's the first thing that you'll get running. The chapter exercise itself, for one, you will print out your name and a counter when you press the button. So there's me, and we're just counting up from there every time you press button 1. And the other thing that you are going to make it do is read characters. And reading characters is actually a bit of a challenge, but when you type, then you're going to get that information into your receive buffer. It doesn't do anything because it doesn't really have anywhere to go, but the exercise is set up so you can actually see that filling up your receive buffer and making sure that that is happening properly. And it discusses one of the other little problems of using terminals, and I'll leave that for you guys to discover on your own. Any questions about UART/RS-232? I guarantee you that you will use this in industry because everything has a UART. Even the iPhone has a UART interface out the cable. Every device I've ever done, even if it's not meant as a main function for UART, it'll have programmers access via UART. Even if it ends up that you're soldering wires on 2 special locations on the board, it's probably going to be there. So get to know it. It's got some problems. It's probably the most common and one of the oldest communication protocols since computers became out there. It's kind of sad that most computers don't have serial ports anymore, but the USB to serial ports cover that off, no problem. Parallel ports are the other thing that used to be out there. I never really used a parallel port. They kind of died for some reason. So you don't see those much anymore, except if they have a really old printer. We good?